Hello, we're Michael, TJ, Lucas, and Levi, and we're excited to share what we've been working on this semester. Our design concept began as a somewhat fuzzy idea for an arcade game. Our stakeholders have many different needs, some of which you'll hear about later on in the presentation, and this was the best solution we came up with to meet each of those needs. So how does it work? Museum visitors will modify a straw to give it some sort of anisotropic property. The straw will be mounted onto the motor, which will move with the press of a button. The motor will press the straw against strain gauges to measure its strength in two different directions. The results will be displayed using Bluetooth for the user to see whether they have created an anisotropic structure. From humble origins, our concept evolved into a fleshed-out manufacturable product. It features all of the same components designed to meet our stakeholders' needs. Note that not all components are rendered here, but don't worry, we'll cover each of them. Our team divided and conquered to create each of the subsystems needed for our project to come together. We ended up using nearly all the ports and pins on our board. We ended up with a fairly complex schematic, as you can see. Since it's not easy to read or understand from this bird's eye view, let's take a deeper look into each subsystem and the needs they fulfill. This is our PSOC with all inputs and outputs visible. Beyond being the quintessential piece of hardware for EGR304, our project needs this board to pass signals connecting user inputs with the product's outputs. The power supply system features a switching voltage regulator, power indication lights, and even a voltage sensor input to the PSOC. It fulfills our users' needs by providing long-lasting power and expediting setup. No batteries to charge, just plug and play. The strain measurement system is composed of strain gauges and their amplifiers. These amplifiers have an adjustable gain that we tuned to the 3 to 5 volt range and passed into our board's ADC. This system allows us to highlight the anisotropic properties of materials by measuring real-world force. Our user interface system is composed of push buttons, potentiometers, and LEDs. These common items allow the user to intuitively control our product and provide familiar feedback in return. The limit switch system is composed of two infrared emitter detector pairs and their amplifier. We used a beam break rather than presence sensing configuration to detect when the motor has reached its limits. Beyond fulfilling a requirement for an analog sensor, this subsystem is really about safeguards, both for our users and our product itself. And finally, the stepper motor. From the very beginning of the stakeholder interview process, it was clear that motion would be a critical requirement of the project. The stepper motor allows us to move in two different directions, which is essential for measuring anisotropic stiffness. But best of all, the motion of our system is what creates the fun and engagement for our users. With so many parts and pieces, our PCB ended up pretty cluttered, with nearly all of the available space being taken up by components or traces. However, some neat routing and soldering allowed us to fit everything on. No good hardware is complete without software. Our PSOC runs a very simple loop. It waits for the user to press the start button. It then moves the motors to press the straw against the strain gauge, reads the force values, and sends them to the user's phone via Bluetooth, then starts all over again. We hope you've enjoyed our presentation and our product. Thank you for watching.